all the joys that we can have together. Well, perhaps there is a typo. Let's think about it before we do anything. So the question you asked is, well, first off, there's two things. Is there a typo in what I wrote, or is there a typo in the problem? Or is there no typo at all? So what we need to do is we need to first think about this. Let's ask ourselves, is the problem stated correctly? Now, you as the student is going to say, well, how am I supposed to know? Well, one way to know and ask yourself if something's stated correctly is no matter how many times you try to do it, you just can't seem to get it correct. That's one way that you might think something's wrong. Then you might say, is O'Grady lying to us? Or is he doing what he likes to do when he tries to trick us? You know, there's lots of sort of different scenarios that can come from this. And so what you guys need to do is remember, and now, Jared, you've never had me for class, but some of these students have. And I've been known from time to time to do that, ask you to do something that's false or not true. Don't forget, one of the most important things in mathematics and in science is you can't solve something that's unsolvable. You can't verify something that's false naturally, right? Now, how does science work? We pose questions and say, is this true or is this false? And then,
I'm wrong, though.
Are.
What's that?
Oh, since there are three propositions, are true.
Well, okay, that's the joke. I get the grammar typo. Oh my God. Thank you. That is good, though. That was very good. Yes, clearly, yes. Okay, you get that joke. But that's not what I'm talking about. Oh my God, that was actually, I was wondering.
There is a typo, I just said.
What? I know. Oh God. It is fun though. I'll tell you what, this is why I enjoy my job. It is fun to mess with you guys like this. So, okay. Now, that being said, and I'm guessing, Jared, you're referring to the actual statement of the problem because you said something about an and or an or. So the question that Jared's asking is did I write this sort of distributive law down correctly? Is it stated correctly? Now Mackenzie's changed her tune. She is now confident that Jared is correct.
Yeah, I'm terrible with writing things down.
You're terrible with writing things down?
Yeah, I copied it wrong, so my homework was right, but it's not like that.
So, see, that's the best. That's the talk about the imposter syndrome of the century. Now you think that you felt real good with your homework, and then now you're like, damn. Jared seems smart and he thinks there's something wrong. You know, you ever do that? Like when someone asks a question in your mind, you have this stereotype of whether you think they can be right or wrong, right? You're not supposed to do that, but we do it naturally, I believe, right? Isn't that sort of what we do that naturally? Okay, so, let's be very careful with how we do this. We would imagine that there should be some symmetry, right? So what I think what Jared's pointing to is when you look at the right-hand side of this statement over here, it doesn't look symmetric like we'd imagine it. Because if we're calling it a distributive law, let's remember, just for the sake of an argument, what is the first distributive law you ever learned was this. It was if you have A times the quantity B plus C, for real numbers, this was AB plus AC. That is the distributive law. Right? So the way I always tell students to imagine it is you are giving A to everybody inside the grouping, right? So if we go purely on the analogy here, and we think about distributing sort of this P to everybody in the group, you with me here? Then we would imagine it would be P and Q, which this meets that, right? Checks. And then it would be the operation inside the parentheses, which here is or, right? And then it would be P and R, if we're going strictly over the analogy, which means the way that I've written this here, and also the way that it's written in your homework is what? Incorrect. Now, I'm going to stereotype Abdullah now because he's been a good student in my experiences, and I'm going to assume that the reason he asked about this problem, that he couldn't get it correct, and that is because he realized that the problem was stated incorrectly, but he did not want to insult me. So instead of asking, was it incorrect, he just said, can we go over it? Right? I'm just kidding, by the way. But no, but this is in fact true, right? So look, you have to understand, now to be fair, maybe you should argue I could have stated the problem differently, said, is the following equivalent? Yes or no, right? And then, but again, you have to, one of the big issues in a class like this that and going forward for students is you guys just tend to think things are true in your mind, so you just say they're true. Or like a good example of how what I mean by this is go back to Calc 1. If you remember in Calc 1, we would always ask you at least once on a test to use the definition of the derivative to compute a derivative. Now, what many of you would do is you would be afraid of all that algebra and the limit stuff, and you would just write limit, a bunch of blah, blah, gibberish. And you knew what the answer had to be, so you would just write a bunch of gibberish from the beginning to the end and just write the answer, right? And then in your mind, it's correct because you know the answer is correct, even though the gibberish you put down is not. So what will happen on a problem like this that I give is that you just assume, since I wrote it that way, that it has to be correct, and then you just fill in the details to make it correct, even though there's no logic behind it, right? And that's a problem. And that's what we're trying to point out. It's also fun to do this because some of you will go on the internet and find the solutions to the last time I taught this class, and you'll copy the same BS down to someone else who didn't know there was a typo does. One of my favorite things to do. You know, what's that stupid website, oh, you guys pay money, Chegg? I saw my stuff on there. I was like, who's paying for my homework? I'm going to have to work harder at it. All right, so anyhow, let's carefully do this now. Are we okay? We on the same page? The problem is stated incorrect. So let's make a very important note of this, and I hope you're paying attention at home. So note, the problem should read, it should say P and the quantity Q or R is logically equivalent to P and Q or P and R. So that's what you should definitely pay attention to. Are we clear on that? Any questions, comments? I do love it, said Mackenzie. That was the best answer. Oh, I did it wrong.
Well, technically, I wrote it down wrong, and I did it right.
I had a professor once. This was great. On our midterm for a class similar to this, they said, prove the, if you look at homework 1, I said state the De Morgan's laws and then verify them. But I had a professor once that said, show the following De Morgan's laws are correct. And then what he wrote down and asked us to show weren't De Morgan's laws. They were just random things. And then he was mad at none of us, or at all of us, because only one person realized they weren't De Morgan's laws. And he's like, how? And that just shows to you that what we do for tests. We prepare to pass a test. We don't prepare to think about what we're doing, right? That's all we give a damn about. And that's not necessarily our fault, because that's what schools taught us our whole lives. You got to pass these tests. That's the only way to make it in this world, right? Jump through all these hoops. But what he was upset about was similar to what, I'm not upset, and he wasn't really upset, but his point being is that instead of thinking about what the problem says, we just jump right in. As soon as we see De Morgan's laws, our mind said, oh, we've done this a few times. Now let's just wrap this off, even though we're not answering the proper question. So sometimes we got to take a step back and think instead of being so concerned about memorizing things. But nonetheless, let's talk about this briefly. And what I'll do is at least set it up for you. How's that sound? It's a big, ugly truth table. You might have to turn your paper sideways kind of thing for this beast, right? So we have 8 scenarios that we have to consider. So the first thing, as I always said, here's the way I would think about this. Let's write it down again one more time just so we can see it. Well, at the top, it might make it a little easier for us. So one more time, we have P. And what one were we doing? And. So we're doing P and Q or R. Has to be the same thing. Equivalently, truth tables are the same as P and R, or P and, I wrote that down wrong. This should be Q. You know, that was an honest mistake. I apologize about this. By the way, this is ugly. This just needs to be fixed. Okay, are we okay with that? Let's just double check that it matches what we did before. Yes, it does. That's exciting. So here's the way I would tell you to think about it. We have three propositions, P, Q, and now R. And that means there's 8 scenarios. So sometimes this confuses students, but imagine a good way to always remind yourself of how many scenarios there are, or think of like flipping a coin. If I flip a coin 3 times, how many different scenarios can there be? How many, and the fancy word for that in probability theory is how many outcomes are there? So I can flip a coin once, I can get 3 heads, right? So same thing here, I might have 3 tails, 3 trues, you know? And then it could be true, true, false. And then it can be true, false, true. So that's the first 3. And then it can be true, false, false. So I'm sort of running through each scenario. And now it can go in the opposite way, symmetrically. Then it can be false, true, true. And then it can be false, true, false. And then, of course, we can have false, false, true. And then the last scenario would be all 3 are false. So what I'm going to do now is draw some lines here to sort of separate this. This is kind of how I like to do it. This is going to be your big boy. Okay, now I told you this last time we did this stuff. What I like to do is I like to write down each piece. I don't like to try to do it all at once. I like to break everything down. So how many pieces do I have to this puzzle? Well, the first thing I note on the right-hand side, I have this piece. I have a Q. Remember, I'm going to work from the parentheses out. Parentheses out. So the first piece I'd have to do here is Q or R. Are we with me here? And then once I have that done, once I have that piece done, then I'm going to combine it with the and P. So I'm going to write this piece in green because this is the one this is the one I want to really get at. Okay, so that breaks down the left-hand side of the sort of the equivalent. Excuse me, now I need to do the right-hand side. Very good, guys. Paying attention. Okay. So now let's break down the right-hand side. So the right-hand side starts with this guy. Then I have to do this guy. And then I have to combine them all. So it's nice to sort of divide these up. And what I'm going to do is just remind myself, I'm going to take my green color out and remind myself that this is the guy. This is the guy I'm after too. I want to make sure this guy and this guy are the same. Now, I don't mean make sure they're the same by you just plugging. Let's wear my mask, I'm sorry. By you just making a match, you need to logically show they match. The idea is to slowly do it. Don't just write it down. Because you can imagine, in theory, I could ask you on a test to confirm or deny something. And then you'd have to be very careful to see if they match. That would be more fun, I think. Okay, so anyhow, let's go. Let's go build this beast away. So what I used to do when I was a student is I would get like a roller. Now, I know you guys don't carry rollers anymore, but I would cover up the thing on the left that I ain't looking at. So what I mean by that is in my first column, I'm interested in Q or R, right? So what I would do is I would put my hand or hide something over the column of P so it doesn't get in my way. Do we understand that? So if I'm doing OR, it's true if they're both true. It's true if one of them's true, and then it's false if both are false. That's how we do OR. Are we cool with that? Everybody okay with that? Now remember, I'm not looking at the far left column. The P column is not involved in this. I'm only worried about Q and R right now. All right, so now they're both true. So that's true. And then again, this is true, and then this is false. So remember, the only time OR is false is if both are false. That's the way I like to think about it. Okay, now we have to do an AND. Yeah.
Shouldn't the second to last one be false then?
So in the what?
The second to last one be false then, since there's two falses?
No. See? But we're not, don't look at the first column. Ignore. So the question was, shouldn't the second to the last one be false?
I thought you meant ignore that side. You meant.
No, I'm saying you covered just the P column. You're looking at the columns Q and R right now. That's it. And we're only caring about Q and R, and I'm covering it up. The only reason we're caring about Q and R, so what I'm saying to you right now for this column right here that we're working on, take a line or do whatever you can mentally cross this creature out, because it doesn't matter right now. Doesn't matter. Once we do this column right here, now it's going to matter again. Right? So now that I've done that, now I'm going to take P, so now I'm going to look at the first and the fourth columns now. So right now, to do this piece, I have to look at, right now I have to look at this guy, and I have to look at this guy right now. Now, I'm doing an AND statement. So the only time an AND statement is true is if both are true. Is that clear? So if I look at it, this is true. The next one, true. The next one, true. And then false. Now, right underneath, we need both to be true. Well, that's not the case. Now we need both to be true. That's not the case. We need both to be true. That's not the case. And then both to be true. That's not the case. So when I say both to be true, that means I need the first and the fourth columns to both be true. So now we need to double check ourselves. Is that, so it's true 3 times and false the other 5 times, we believe. That looks to be the case. Does anybody have a question about this? Comment. Now, there's nothing cool about being fast at this right now. After you pass this class and you move on to other stuff, then you could say, I'm going to be as fast as I can with truth tables. Right now, it's slow and steady. That's like anything. When you're learning arithmetic, it ain't cool to be fast. Get it right. And then once you're out of arithmetic, you can be as fast as you want. That helps you with algebra. And then when you're learning algebra, you go slow and steady. And then once you get out of algebra, then you got to figure out how to get fast, because if you stink at algebra, you're going to have a hard time learning calculus, right? But the point is, you have to understand and then get fast. Don't try to go fast with this until you really understand it. Okay, now we have to do the game all over again. So I'm going to ignore these columns now. What am I going to do now? Now I need P and Q. So what columns am I interested in? Well, now I'm interested in the first two columns because I'm doing P and Q. And so when I do P and Q, I know that it's only true and is only true when both are true. So it's going to be true here. It's going to be true here, and then it's going to be false, 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 and false. So a common mistake that will happen here is sort of, and not to pick on you, Michelle, but you made the mistake, is we get confused which columns we should be looking at. You can only look at two columns at one time. It doesn't make sense to look at any more than two. You have to think about how you're going to do that. All right, now we're going to ignore the first and the second, and we're going to look at the first and the third. So now I'm going to look at P and R. And so P and R, again, it's only true when both are true. So since it's and, this is true, false, true, false. And then here we are false, 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 false. So we only got two truths this time. Does anybody have a question? How about at home? Anybody have a question? I miss you guys. It's so sad. Okay, so now we're going to ignore these columns on the left, and we want to do the final piece of the puzzle, and we hope that we've done it correctly. I'll get my pink out. We are now going to look at these two, because that's the very far right. It wants us to study those two, and we want to do the OR. Before I do anything, I remind myself, what does OR mean? OR means true every time except when they're both false. So when I come over here, they're both true, good. One's true, good. One's true, good, and then the rest are false, 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 false. And we celebrate because the green starred columns match. So the third column, the fifth column and the eighth column match. And so that is a proof. That is a logical proof that they're the same thing. Does anybody have a question about this? So this is a tricky sort of problem, huh? I think so. What if I gave you like 4 propositions? Then you'd have 16 scenarios. That'd be, I mean, there's, this idea of propositional logic, one of the best places on the planet to study it is right down the road at Carnegie Mellon. They have like one of the world's most renowned place for studying propositional logic. Kenzie's like, why would you want to do that? You're right. There's no reason to. No reason whatsoever to study this kind of stuff. Too bad we can't get most humans to be more logical. All right, this is a tricky problem. And for what it's worth, I ain't going to give you one much bigger than this on a test, or I'm not going to give you some insane. We're trying to learn this, so this is about as difficult as they can get. But you should know at least how to do construct truth tables with 3 propositions. I mean, this stuff, again, it's extremely important in programming and particularly computer science, certain aspects of that. You know, you don't have to, trust me, just Google truth tables or Boolean logic. You know, read stuff in the book. All right, does anybody have a question about this? We good? This is fun. I like this kind of stuff. I do. Although it gets you in fights with the I call them the double-digit IQ crews out there. Like, I always argue with Amy when she says, I was telling the class this yesterday, she'll be like, I'm annoyed at you. I'm like, why? And she'll be like, well, you acted like a jerk. And I'm like, give me an example. Verify your claim that I is a jerk. And she'll be like, I just can't. And I say, you tell me I'm acting like a jerk, but you can't exhibit one thing that claims I'm a jerk, right? Does there exist a behavior that made me a jerk, or am I a jerk for all situations? You know, this is what I say in the shop. This is fun. All right, cool. Any other questions about homework 2 before we move on? I know we covered problem 5 on Monday. Don't forget, I post all the lecture slides and the videos to YouTube. So if you ever want to go back and see any of this, it's right on Canvas. You know, need I remind you? I shall, because last semester someone yelled and screamed. So if I take you here, if you just go to Canvas, when you log in, everybody should be seeing Canvas and stuff at home. When you log into the course on the computer, the home page has everything right there. There's the embedded link to the YouTube. You can watch every lecture here. The slides are here, the homeworks, the syllabus, all that. All right. Now, if you log in on your phone, it's not going to look this way. Like if you use the app, you have to, but it's still there. I just don't know how you can, there's not a home page on a tablet, or maybe on a tablet there is, I don't know. But if you look at the app, you probably have to click on one of the, what do they call it? One of the links. So please check that out. It can't hurt to watch them. It's how you learn. Yes.
No class next Monday, right?
That is correct. There is no class Monday because of the holiday. Labor Day.
I had a question on the homework.
Sure, what's up?
So I had that exact, because I noticed that there was a typo, and I had that exact table, and I also had a little side note question. Would that be considered like correct if I questioned the typo?
Oh, yeah. Do you talking about you already submitted it?
Yeah.
Oh, yeah. Don't worry about that. That's
Okay.
the best kind of answer is the one that recognizes there's a typo, bro.
I mean, I did both. I did the
Yeah,
table and that.
Yeah, don't be Mackenzie and act like there's no typo. See, she's playing the wrong game in survivalship bias. She assumes because I am the instructor that I could never make such an error, which on one hand is very much what we call kissing you know what, right? But don't forget that sometimes I am testing you guys, right? Not in a bad way. What's that? Now, what'd you say? I want to know. Well, I want to know so I can tell them. I do a lot of research to understand how I can best educate you, and what students complain about all over the interwebs is when they're at home and then they hear a question in class and they don't know what it is because they say the professor doesn't re-say the question. You notice I try to do that? I say, hey, the question was, see, I am trying my hardest for you guys. Yeah, I'm trying my damnedest. And then Mackenzie is clowning on me, making fun of yours truly.
Not. I just said maybe you're more human. and
Yeah,
you
I know.
make
That is a good
mistakes.
point. Why is that we always think that people can't make mistakes like instructors? Like, what? But there are some instructors that probably would be upset if they made a mistake, or if you call. I'm always thinking, what the hell good is that? How is that teaching people anything? The moment you think you're better than everyone else, the moment you stink, in my opinion. But there are egos out there. There's plenty of egos. All right, we cool? So, Dimitri, was that you? I think that was you talking. I don't remember.
Yeah.
If it wasn't you, I apologize. But yeah, absolutely. If you think there's a typo, feel free. Like, it's funny. In Calc 2, I always do this. I'll give them these problems, and some of you might remember it. I'll say, compute the area of the region bounded by a curve revolved. And no one will ask me, how can I do it, when I'm asking them to do something that's impossible to do. And finally, this semester, after 3 semesters, not even you, Abdullah, asked last semester, and not to pick on you, but not one person said there's not a region because you didn't give me a domain. And I said, that was a different problem, though. This is I know, but you were last summer, right? So you didn't count. Last fall, okay. Well, then that's 2 semesters then, spring and summer, that didn't ask. But no, but that's good. You should always question things, right? Now, there's some people who philosophically say I shouldn't do that because that makes you second guess yourself. But no, I mean, you should be being inquisitive, asking questions, and being curious is the best thing I hope you can leave with. You know, don't let those people tell you not to be curious. You should have seen me. You imagine me in school, I was raising my hand asking dumbass questions all the time, mostly because I like to hear myself talk. Secondly, because I was just curious. I didn't have Google when I was 16 like you guys do now. All right, anyhow. Very good. Okay, so let's pick up where we were yapping about at the end of last class. So we want to kind of transition now. We're going to start treating this as more like a traditional math class starting today. But what we wanted to do was we wanted to transition you from this logic stuff into how it starts to apply for mathematics. That's what we're trying to transition to. So what we did last class is sort of the following. So the question you might, of course, be asking is, why do we even care about logic? And interesting you asked that. Human beings that we know of, at least, have been asking this question since that we know that we have written history. I mean, in the days of people like Euclid and many, many more, human beings were curious about how do we logically verify something. Just because we see something with our eyes, how do we logically verify? When we look at the stars and the planets at night, how do we logically verify that in so many days that planet will be there, right? How do we know these things? How do we know that if we add 2 rational numbers together, we get a rational number? Our intuition tells us things like this, but how do we verify? So that's why we care about logic, because it is the basis for many things, but for us, such as mathematical proof, and computer science. Now, again, this is a math class, but most of you are familiar with computer science and the courses and programming, at least at an elementary level. And so we're going to try to make connections that were applicable, but there's almost everything that we're going to do in this class is applicable in some way or another to not just programming, but the science of computers, the science of software and computer engineering, and how do we program. An interesting thing that's sort of not related, but when I was in college, I had a lot of friends who were going to law school, and they had to study. To get into law school, you have to take this, it's called the LSATs. It's like a law school SAT type thing. And there's a whole section on it, which is all logic. And if you can do this kind of stuff, you will ace it. Because they'll ask you all kinds of things like I did on that homework, sort of like every computer science major takes discrete math. Abdullah is in discrete math. Therefore, Abdullah is a computer science major, right? Is that true or false? Can we conclude that? And as you guys know, the answer is no. Just because you're in here doesn't mean you're a computer science major. Those kinds of things, following reasoning. And so what the propositional logic is all about is developing the rules for what we're going to call the reasoning. And so for example, many sort of statements, or as we said, the way you should think about them is these theorems are of the form, say P implies Q, P if and only if Q, maybe P and Q implies R, excuse me, implies R. Etc. And so what the logic does, so not the logical, that's a bad way of saying. The logic gives us the rules for proving them. Do you understand what I mean by that? So if a statement says if P then Q, so if a function is differentiable, then it is continuous. Well, how do we verify that? What does it mean to verify that? So in a calculus class, we do this little hand wavy proof where we write out limit and we show that if you're differentiable, you also satisfy the definition of continuity. But from a logical standpoint, what does that mean? Well, think about the truth table for P implies Q. When is it true? The conditional P implies Q is true when both are true, the hypothesis and then the conclusion, that makes sense. And then they're also true if you lie and then tell the truth when P is false, and then they're only false when you don't make a promise. So if you think about the truth table for P implies Q, then that gives you sort of the rule book or the sort of the instructions on how to verify a theorem P implies Q. And if you look at things like logical equivalence to these statements, then there's rule books on how we can verify things. And we did that in two basic examples on Monday. So let's remind you of that. So on Monday, we proved a couple P implies Q statements, and I'll write them down in English. You might remember what we did. So we said if n is an even integer, then n squared is even. And then, of course, we proved also if n is an odd integer, then n squared is odd. So how did we prove them? We proved them by assuming the hypothesis P was true. And then we deduced through a series of what I guess you can call algebraic or arithmetic sort of equivalences or equals signs that Q was also true. And since P is true and Q is true, the truth table tells us the statement must be true. So let me remind you of that. So we did this. And So thus, the statement P implies Q must be true. And the reason that that's the case is, look at the truth table. So I'll just remind you of what the truth table looks like for P implies Q. You have P, you have Q, and then you have P implies Q. Since there's two, there's four scenarios: true, 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 false, false, true, and then false, false. And this is always true except when you lie. So think about these sentences. Think about both of these statements, 1 and 2, in terms of this truth table. So let's read number 1 under the top truth table, the TTT. So what I showed is I assumed P was true. And then through a series of equivalences or inference, yes. Uh-oh. Zoom, zoom, crash, crash. Not good. Oh, yeah, we lost her. We'll bring you back. We'll bring you back, Harley. So we assumed P was true. Then through a series of inferences, through a series of algebraic reasoning, we showed that Q is true. And since the truth table says that means the statement's true, we have successfully proved it. Now, imagine the second scenario where we assumed n was an even integer, that's P, and then we deduced that n squared was not even, it was odd. Well, there's no way to do that because it's false. So that scenario doesn't even apply to us. Correct? Now, suppose we did the other scenario. Suppose we had a statement where we said P was false. So, and then we tried to show that the conclusion is true. Well, if the conclusion is true, it doesn't matter what we tell you. That goes back to the thing about you in school. I can say anything I want. Here's a ridiculous thing I can say. Ryan is 40 years old. Abdullah is in discrete math. Therefore, Abdullah is in discrete math. Did I lie to you at all? Even if I change the premise, even if I say O'Grady is 12. So if I say, if O'Grady is 12, then Abdullah is in discrete math. Well, guess what? You're in discrete math. Does me being 12 or being true or false have anything to do with you being in discrete math? No, it's still a true statement. So the implication's got to be true. Do we understand this? I think maybe. Yes, Mackenzie. Well, that's exactly right. The second scenario is the only time you promise something and don't fulfill your promise. So the good example is, if you get an A on the final, you'll get an A in the course. The only way that I can lie to you, the only scenario where I lie to you is that you get an A on the final, but you don't get an A in the course. Then I've lied to you. I've broken a promise. And any other scenario, I can't. Because in the case you get an A on both, then good. In the case you don't get an A on the final, maybe you get a B, but I still give you an A in the course. You still got an A in the course, right? And in the case that neither one of them happens, well, then you can't be mad because you didn't meet the requirements. I didn't break a promise. You got a B and a B, right? Makes sense? I love saying makes sense. You're like, no. No, you actually, everybody does this. They're like, yeah, I got it. 3 hours from now, you're like, what the hell is he talking about? That's the old understanding versus recognizing dilemma that students get themselves in. Okay, so very good. Here we go, though. Let's note that sometimes we might use sort of the rules of logic differently. So let's illustrate this with another very important sort of number theory problem. Let's consider this statement. Number one, if n squared is even, then n is even. Or the English sentence that says the same thing, the integer n is even whenever n squared is. So that's two ways to write the same sort of statement. So both sentences make the same claim. Question is it true? And then if so, why? I'm gonna lose my mind with that ice water. I hate it. I can't even go to the cafeteria and get some. Okay, so here's the thing. You might say it's clearly going to be true because you'll say, let's take a squared number that's even. Do you have any numbers that are squared that are even? Say 16, that's even, right? What's its square root? 4, checks out. 64 is even. Checks out because 8's even. 144 is even. Checks out, the 12's even. So we think it could be true, but how do we prove it? How do you take a number and say it's even and then prove directly? So let's say something here. So it turns out it is not easy, and I'll put that in quotations, to prove that P implies Q here. And the thing is, you might say, well, since I can't do it, then maybe it's not true. Like, again, when I say prove it that way, that would mean take n squared and say it's even. So that means n squared equals 2 times k. So let's try. So let's just try. So let's assume n squared is even. Now we know what that means. From last class, we know the definition of an even number means this means that n squared is equal to 2k for some k. In particular, we know it has to be an integer. So the problem is that how can we show n equals 2 times some j? So you might say, well, take a square root, right? You might say, well, then let n just be the square root of 2k. Well, how do you know that that number is an integer? You don't know that. So what do we do? Does anybody have any ideas, thoughts? Does anybody have any thoughts? So it seems like we're stuck. So perhaps we use what we say an indirect method. And the key observation is to recall that P implies Q is logically equivalent to what we call its contrapositive. Its contrapositive is not Q implies not P. So since we have these rules of logic and we know that these two things are equivalent, we might try to prove it this way. And it's going to turn out that this way is much easier. Perhaps you could have figured something out that's in the green. Perhaps. But it wasn't as easy as the ones we did on Monday. The ones we did on Monday fell right out. You assume something to be true, you do a little algebra, voila. That ain't happening here. I mean, you could take a square root and say that n is the square root of 2k, but how can you deduce at all that that's an integer, let alone an even one? I mean, you guys know that the square root of most integers isn't even a integer. I mean, the square root of 4 is 2, right? Square root of 9 is 3, but what about the square root of 13? Is that necessarily an integer? Absolutely not. So this is what's called a indirect method of proof, or proof by contrapositive or contraposition. So let's try it. So we're going to look at the different perspective here. So what was our original P? Our original P was n squared even. Q was that n is even. So then what does not Q mean? Not Q means n is odd, correct? And then not P means that n squared is odd, because the opposite of even is odd and vice versa. And here's a cool subtlety. By our definition of even and odd, it's impossible to be both. You can't, obviously, an integer has to be one or the other. It can't be both. So what we're saying in English, we're saying P implies Q is equivalent to not Q implies P, excuse me, not P. So in English, this means n squared even implies n even is equivalent to n odd implies and squared odd. But we proved that exact statement Monday. So let's make a note of that. We proved this Monday. What a time to be alive. I'll tell you what. I have to go in my empathy mode and remind myself of how lost and confused and how stupid I felt when I was sitting in a class like this. Much like some of you feel right now, lost and confused, and you feel like you're not smart, right? And you say, how do these people get this? I don't get it. Right? Everybody is lost right now. That's okay. And right now you're saying, no, I'm not lost over it. This stuff is a whole new world. Well, that's when we should sing like the Aladdin song. A whole new world. It's where we'll be. I did that one year. I think it was we stated, that's right. We stated Taylor's theorem in Calc 2, and I said, use a whole new world for you now. And then we sang it. We put it on the original cartoon, not the Will Smith version, I like the cartoon version. Good old Aladdin. It's Mike as a kid. Oh, there's probably like a lot of cultural appropriations taken in. Which always reminds me, the one business that gets away with stereotypes and appropriating cultures better than anyone, and I don't want to say better because that's a bad way, is wrestling. You ever watch wrestling? Boy, they beat the hell out of stereotypes and they appropriate cultures, but no one ever gets mad at them. I guess maybe some people do. Anyhow, what the hell are we talking about wrestling for? You say, I wonder? Come on now, it can't be all that bad. I watch wrestling a couple times a year. And I'm an adult. Okay, so here we go. So this is in fact true. We now know that anytime you have a number whose squared is even, we automatically know that the number itself had to have been even. So this is a very, very useful trick, is that it's like, and I've mentioned this many times before, even in other classes. Sometimes all it takes is to change your frame of reference. And then when you see something from a different angle, all of a sudden you're like, and there's really, there's no sort of substitute for that. When you're problem solving, sometimes if you keep trying something and beating your head against the wall, sometimes you need to step back and look at it from a different point of view. And with these, you know, if we build up our logic and we understand that certain things are equivalent, then that gives us multiple ways of viewing the same thing. And that's really, really useful. So I hope that that makes sense, and then maybe you can sort of go with it and make some more sense. We're going to give you some practice with this stuff. And we might say prove this directly or prove this by contrapositive or something like that. All right. So another useful thing, and it's almost time to go, but we might as well state this, the scary part, and then we'll go right away into to a proof, and then we'll be done. So here's another sort of indirect proof that relies on something. So let's note that Q and not Q. Think about the truth table here. Can this thing ever be true? Well, no, because and is only true when both are true, right? And this doesn't make any sense. So what happens when something is always false? We call it what? So we sometimes we call that a contradiction. All right, now let's look at another statement. So let's take the following. Let's take not P, okay, implies this, Q and not Q. So let's think about what this says. So we know that the ending is always false. And so if we can show so again, ponder this for a second. The implies part is always false. So if we get not P implies something false, so then let me be a little, let me say this a little clearer, and then we're going to get out of here. We'll show you how to use it. So maybe this is going to be a little more difficult than we want. So let me rewrite it a little bit differently. So then, if this guy is true for some P, we know, not for some P, for some Q, excuse me. Sorry about that. Then we know P is true. So what this does is this gives us a way of logically showing something is true by assuming it's false. So let's put this in English. This is called so this shows us how to prove something is true by assuming it's false. Now that might not make any sense to you right now, but here's the idea. So Abdullah comes to me and he says, I have something, I believe it to be true. So I say, okay, here's how I'm going to verify for you, dude. I agree with you. What I'm going to do is I'm going to assume it's false, and then I'm going to use logical reasoning to show that if it is false, I get some ridiculous statement, like 1 is equal to 10, or dogs fly, something like that. And then once I get a ridiculous statement, I know then that your assumption that it was false is ridiculous, so it has to be true. And you might say, well, you're just making stuff up now. Well, no, I'm not. The logic says it's sound. The logic says it's sound. So we're going to do a famous example next week, but let's just state it, and maybe you can start working on it. So the famous example dates all the way back to the days of Euclid, if not further back. Who knows who else figured it out? Square root of 2 is irrational. So to prove this, we assume it is rational, not irrational. And we'll have to define these terms again. You might forget them. And show that leads to a ridiculous conclusion. And so these are called, and again, this dates all the way back to as far back as we have written history. This is called a proof by contradiction. If you want to Google it. All right. Does anybody have a question? I know we went over time. I'm sorry. I'm breaking the rules. I apologize, but it's fun learning. Sue me. Write a letter to the people in charge and say O'Grady is running us over. All right, guys. Thank you very much. I appreciate it. Hopefully, I'm going to post a homework for you later today. I will